Can you see my slides?
Yes, sir, we can see.
Fine. So take down the systems with variable thermal conductivity. So up till now, we have talked about the systems where K was considered as constant. So K, up till now we have not considered this as a function of temperature. So this is what we did up till now. But now we are going to consider K as a function of temperature. Fine. So draw this diagram first. So this is the case of a slab having so this is a slab having temperature T1 on the left face and temperature T2 on the right face, right? So we talked about this case. When K is constant, we know the temperature distribution is linear in slab, right? I hope you know this. Temperature distribution is linear in case of the plane slab when K is constant. So now we will consider the case where you can have either the convex or concave kind of temperature distribution. Now, why this kind of temperature distribution will occur? So we will talk about this term beta and this K naught. K naught is the thermal conductivity of the material at 0 degrees C, right? And considering this and this coefficient beta, we will calculate K, which is function of temperature T, and this K will be used to find out the heat transfer, right? Variable thermal conductivity. So for this, I am going to use this formula. Q is equal to minus Ka dt by dx. So this K is represented by this expression. K is equal to K naught into bracket 1 plus beta T, right? So K naught, I already told you what is K naught, and beta is the coefficient of expansion. So Q is
Sir,
minus K naught. हाँ बोलो.
सर आपने वो K is not equal to f of t क्यों निकाल कर?
See, we have not considered this up till now. So K, we said that K is independent of temperature T. This is what we assumed up till now. Now we are assuming that K is function of temperature. That's why this functional relationship is taken into account. K is function of, this indicates K is function of temperature. Clear? Hello? And this
Yes,
functional relationship is established using the two things, the thermal conductivity at 0 degrees C and this coefficient of the volumetric, this coefficient of expansion, beta. So using these two, we have defined what is K, thermal conductivity. So same thing I am using here. Instead of minus K dt by dx, I am writing K is replaced by this term. Clear? Now, I'm going to use the variable
Yes.
separable method. Use the variable separable method. So you know how to use the variable separable method. I did not have to explain it in detail. So Q by A integral 0 to L of dx. So this dx is taken on the left hand side, and the limits will be this x is measured in this direction. At this level it is 0, and this is the length of your slab or thickness of this slab. So at this location it is L. So that's why limit is 0 to L dx minus this term will remain as it is into dt, and the temperature limits are T1 to T2. We know this, T1 to T2. Now just solve this. So you will get this expression. Now this minus sign is replaced by plus, and this order of the limits is changed. T1, T2. You can take it as T1 on the upper limit and the T2 as the lower limit. Minus sign is taken care here. And once you solve this, you will get this expression. Now from this, you can write this equation. QL by A is K naught into this term. So this bracket is just expanded here, nothing big. Then there are some adjustments like this. QL by A. Now K naught into T1 minus T2 is this whole term is taken as common from these two terms. So K naught into T1 minus T2. What remains inside bracket is 1 plus beta by 2, or beta into T1 plus T2 by 2, this term, right? We are going to substitute for this term now, T1 plus T2 by 2, right? So this is average temperature of this slab, T1 plus T2 divided by 2. So we will call it as the mean temperature Tm. So Tm is defined as T1 plus T2 by 2, and I am going to substitute it here, Tm, and then if I substitute it here, you will see that this term This K naught is multiplying factor for this bracket as well as this, right? So what I am going to write is Km. I am going to define mean thermal conductivity Km, which is equal to K naught into 1 plus beta Tm, right? So for Tm we have substituted this, and then for this whole term we substituted Km. So this is how the whole expression will change to this form. So the rate of heat transfer Q will be equal to Kma into T1 minus T2 by L. So this A is taken on the right hand side. So you can write the final expression for the rate of heat transfer Q. So this is similar to your first case, that is systems with constant thermal conductivity. So if I say that let us say K is constant, right? So if K is constant, this Km will be replaced by simply K, right? So that time you will get the same expression which you derived for the case of constant thermal conductivity. So the same expression can be written like this: T1 minus T2 whole divided by L by Kma. So this L by Kma is nothing but the thermal resistance
conduction.
and delta T. So same expression, Q is delta T by R thermal resistance. And we know the thermal resistance of slab is given as L by Ka. But when K is variable, you will write it as L by Kma. Is it clear? Where Km is the mean thermal conductivity, right? Which is based on mean thermal conductivity, which is based on the mean temperature, Tm. Correct? So
Sir, what is this beta, sir? Beta significance.
So beta values will be given to you. This is a coefficient which is different for different materials, right? So beta may take values positive, 0, or maybe negative, depending on the material. For different materials, values are given in the literature, right? So for constant K, we have substituted beta equal to 0. Then this K is equal to K naught. This will be 0. Then you will get this distribution, this one, which is equal to our previous case, right? And when beta is positive, you will get this kind of distribution. So what do you call this as? Concave or convex? This one?
Sir, convex.
Convex. Is it convex or concave? And if beta is negative, you will get this kind of distribution, right? That's all about the system with variable thermal conductivity for plane wall. So remember, when you are solving the problem of variable thermal conductivity, you have to use this method, variable separable method, and treat K as a variable with respect to temperature T.
Sir, sir, you want to say that in case of that convex type, beta will be positive, and in this beta will be negative in concave, like that.
Depending on value of beta, this will change. Beta will be different for different materials. You can have positive value, you can have negative value, or you can have zero value as well.
Yes, sir.
Fine. Now solve this one.
Sir, if beta is 0, sir, then the graph will be linear, na?
So when beta is 0, K is K naught, means K is constant, no? Correct?
Yes, sir. Yes, sir.
Now take down this. A composite slab 70 mm thick is comprised of two layers of materials A and B. Now for the sake of simplicity, just showing you the diagram itself. So this is a composite slab which is made up of two layers, layer A and layer B. So what they have given is the thermal conductivity in this layer, first layer, is varying like this. So K is 0.5, 1 plus 0.008 T. This was the temperature, this variation in the thermal conductivity for this zone A, where temperature T is taken in degrees. Fine. Now, the layer B has a constant thermal conductivity of 30 watt per meter K. So this value is given 30 watt per meter K. This is constant. And is 20 mm thick, which is written here, and this is 50 mm thick. We already noted down. Then the exposed surface of layer A is effectively insulated. So this is insulation. Whatever these lines I have shown now, this is insulation. Means no heat transfer will take place in this direction. Insulated, and that of layer B is exposed to convection, this side. And what is given about the convection is the environment temperature is 20 degrees C, so this temperature is 20 degrees centigrade, and the heat transfer coefficient is 12.5 watt per meter square K. Right. Now the interface temperature between the two layers is 80 degrees C. So this temperature is given. This interface temperature is 80 degrees C. Fine. Determine number one the steady state heat flux, means what is this Q dash, what do you call it? Q double dash, no? For heat flux, Q double dash. So it is Q double dash is Q by A, right? Heat flux, then the maximum temperature in the composite slab. So you have to find out what is maximum temperature, and then the distance of a plane from the insulated surface where the temperature is 90 degrees. Means you have to find out the location where temperature T will be 90 degrees C. So you have to find out the distance x. This is what the problem is. Is it clear? Hello.
Yes.
So in this zone, K is constant. So as the temperature on this side is low, right? And this is 80 degrees C. So if I try to plot the temperature distribution in this zone, it may look like this, right? And then the convection further, correct? So this is linear temperature distribution, but here it is different. So here in this zone, it is not linear. So depending on value of beta, so beta is positive, right? So what kind of temperature distribution you may get here? It may be something like this, right?
Yes.
Correct? So your job is to find out the steady state heat flux first, then the maximum temperature in the composite slab, and the distance of plane from the insulated surface where temperature will be 90 degrees. And how to solve this? The same diagram I have taken further. See, you can use this now. So Q double dash, that is heat flux. This is temperature difference delta T divided by R total. This is R total. Now I am applying this formula only to this slab. Reason being, I know this temperature. So let us say this is temperature T2, which is known to me, and with T infinity here, right? T infinity. So I am applying this formula for this layer B plus the convection taking place on the right hand side. So I have two resistances in series: conduction resistance of slab B plus convection resistance. So R conduction 2. So if I call R conduction 1 for this, this will be R conduction 2, and this is R convection, right? So I can write T2 minus T1 upon R conduction 2 plus R convection, this one, right? Now Q double dash is written, means this term is Q by A. The area is assumed to be the 1 meter square, let us say. So this is Q by A, this side. So that's why from here, if I write A, that A is taken here on the left hand side. So instead of writing LB by KBA plus 1 upon HA, I am writing only LB by KB plus 1 upon H. That A is taken on this side, correct? So this formula I can use to find out the Q double dash. Are you getting my point or not? Hello?
Yes.
Find out this heat flux Q double dash, which is the first point they have asked you to do.
743.8.
Very good. Just a minute. I will write it. 7. Good.
743.8.
Watt per meter square, right? Now, once you know the heat flux, then what you can do is you can consider this layer now. This layer. And you can use that formula which we have used in the last derivation. Q is equal to minus K dt by dx, right? So that K will be replaced by this term, correct? Formula So now we are finding out flux, that's why that A term is not written here. So it is taken on the left hand side. So I am writing Q double dash is minus K of T. K is function of temperature. It is not K into T. Remember this. So dt by dx is minus K naught. Now this K is replaced by K naught 1 plus beta T term, right? And dt by dx is written as it is. So this is your equation. Now you have to integrate this equation with the limits. Now what are the limits or what are the conditions for integrating this equation? So we have two boundary conditions now. At x is equal to 0, temperature T is equal to T1, and at x equal to L, temperature T is equal to T2. So we are talking about this part, only this thickness. So at x equal to 0, let us assume that temperature is T1 here, and at this level it is T2. So at x equal to L, this is only length, L I am talking about. So when you use these limits of integration and put it here and solve this further, now I am not writing the steps in between. I leave it to you to calculate this. You should get this equation. Because T2 is known to you, right? T2 is known to you. How much it is? 80 degrees, right? So if you integrate this equation and put all the values in this expression, then you will get equation in terms of temperature T1. Quadratic equation in terms of temperature T1, right? Hello?
It cannot be directed. It's the final equation that we derived.
Huh?
Can't we use the final equation that we derived earlier?
Which one? This one? Okay.
No, so let me. So that Q equal to Km A into T1 minus T2 by L, sir.
See,
Q by A को double dash करे तो.
What we have to find out is, you are saying, can we use this equation?
Yes, so Q by A ले ले मतलब वो जो A उधर है उसको लेके मतलब Q double dash equal to Km into T1 minus T2 by L.
Use it and tell me what value of T1 you get. You should get same expression. I just explain you how to integrate between limits using these two.
Yes, sir. Yes.
So you should get this, that the temperature T1 is this temperature is 121.21 degrees C, and it should be the maximum temperature. Now why this should be maximum temperature? Any guess?
Because सर ये starting का है ना सर वो मतलब heat flow वहीं से हो रहा है तो वही maximum रहेगा.
Because there is no heat transfer in this direction. This is insulated. So the maximum temperature will be observed at this space only, right? So you will get T1 as 121.21 degrees. Fine. Now, once you know this temperature, then you can take the point where the temperature is defined as 90 degrees C, and we have to find out what is this x distance, right? So now this time you have to integrate the equation with this as one of the boundary condition or limits, and this as the second limit, right? So previously we integrated equation between these two faces. Now we have to integrate between these two. So you can integrate the same expression again, and you will get this type of equation. So where x you have to find out. Q double dash is already known to us. Beta is known, and this T1 square minus T square and this T1 minus T terms you will get when you solve this integral. So T1 is already known to you, just now you calculated, and T is the temperature, this is 90 degrees, correct? So if you put this 90 degrees C, T1 is known to you, 121.2 degrees C, beta is given, I think 0.008, and K naught is also known to you, right?
Sir, this x is only L na that we will be using na.
X is the distance. X is the distance where the temperature will be 90 degrees. So when you integrate, you should put the limits like at x is equal to 0. At x equal to 0, temperature T is T1. This is one condition. And second, at x equal to x, temperature T is equal to this 90 degrees C, right? So use these limits and then integrate this equation. You will get this result. And now from this equation, the only unknown is x. So find out x. So you should get this answer. So x is 0.0397 meter. So 39.7 mm. So this is 50 mm. It's 25. So somewhere here you will get. So this will be the location where the temperature will be 90 degrees. Right? And as this part is insulated, now the temperature distribution should look like this. This should be the highest point, and then you will draw the temperature distribution like this. Like this. And from this point onward, you can say this is varying like this linearly, and then the convection part. So this is how you should show the temperature distribution. Clear? Hello?
Yes, clear.
Can I go to next slide now?
So we are solving it right now.
Okay, solve. Right now, getting the exact values is not important. What is important is you should understand what should be done and how you should start this, from where to begin, and why to begin with slab B only. That kind of questions you should try to answer. Now you understood why we started from slab B only, or the right hand side of this problem, because the data is
Yes.
on that. Right? And that is the only way by which you can find out the heat flux first. And once you know the heat flux, then you can do the rest of the things. Similar to our composite slab, composite cylinder, and composite sphere. The only thing is air K is variable. You have to take into account that. So use the variable separately and integrate the equation. Finished? Now only to save the time, I am not writing the steps in between. So here I am assuming that you are well conversant with all these steps. That is how to take the derivative and integral. This is the prerequisite for this subject. I hope you know partial derivatives, first order, second order differentials, how to integrate the equations, how to take down the derivatives, first derivative, second derivative. All that stuff, I am assuming that you are well conversant.
Yes, advanced.
So we'll talk about the systems with the variable thermal conductivity. Second case is the hollow cylinder. Now same logic is applied here also in case of hollow cylinder. So what we started with is Fourier's equation, considering K as function of temperature. So I am writing Q is minus K naught 1 plus beta T A into dt by dr. So instead of dt by dx, it is dt by dr. So K is K naught 1 plus beta T, and this area A in cylindrical system, this will be 2 pi RL, surface area of the cylinder. I hope you know L is the length of the cylinder. So remember what is this? Now, I leave it to you to derive the equations. I am just directly writing the equations on the screen. So using variable separable method and integrating equation 1 and using this substitution which we have already talked about, that mean temperature is T1 plus T2 by 2, and second substitution Km is K naught into 1 plus beta Tm. You should get this equation for the rate of heat transfer. That Q is 2 pi Kml Q1 minus T2 divided by Ln R2 by R1. Right? So R1 is the inner radius, R2 is the outer radius. So the same expression can be written like this. Q is this T1 minus T2, which is delta T, divided by 1 upon 2 pi Km Ln R2 by R1. So you can write the expression in this form, right? This is nothing but delta T by R thermal resistance, correct? So this is thermal resistance, we know. I missed out L here, 2 pi Km L. So this is your thermal resistance. So do you remember when K is constant, how we used to write the thermal resistance? 1 upon 2 pi KL Ln R2 by R1. So here K is replaced by Km. Is it clear?
Yes, sir. इसका डायग्राम नहीं है क्या?
Can draw the diagram. For can I go to next slide?
Yes, sir.
Solar sphere case. So same expression, Q is minus K naught 1 plus beta T A dt by dr. Now here, this K is same, whereas this A, the area for sphere, the surface area of the sphere is 4 pi r square. So this A should be replaced by 4 pi r square. Again, the same procedure, use the variable separable method, use these two substitutions, that Tm is T1 plus T2 by 2 and Km is K naught 1 plus beta Tm. You will get this expression for the rate of heat transfer. Q is 4 pi km T1 minus T2 upon this term. Or you can write this equation as Q is equal to T1 minus T2 whole divided by 1 upon 4 pi km 1 upon R1 minus 1 upon R2. Or you can write it like this, 1 upon T1 minus T2 upon is it correct? 1 upon 4 pi km. Correct, no? R2 minus R1 upon 4 pi km R1 R2. So this is nothing but your, or this term is nothing but your thermal resistance for the spherical system, right? I hope you know this. Do you remember it or not? So only K is replaced by Km. Rest of the things are similar to our constant K case, right? So I am not spending much time on this variable thermal conductivity. So only one thing you should remember is whatever you want to calculate, you should use the integral approach only, variable separable method only when K is variable. Remember that. Now can I go to next slide?
Yes.
Now moving further, we will talk about one-dimensional steady-state heat conduction with energy generation or internal heat generation term. So up to this point, we have neglected Q dot. What is Q dot? What is Q dot?
Q by T. Q by T is the rate of change of heat with respect to time.
Q dot is volumetric heat generation rate. So unit of Q dot is watt per meter cube. Correct? Volumetric heat generation rate. So we have neglected that term. So now from this point onward, we need to consider the first case. So the plane wall. Let us talk. Let us say this is case one. So we are going to discuss three cases of plane wall itself. So case one I am just explaining here. So our starting point is our heat diffusion equation in Cartesian coordinates in its most general form. So you should write this equation again and again so that you remember this. So dou by dou x of k dou t by dou x plus dou by dou of k dou t by dou r plus dou by dou z of k dou t by dou z plus q dot, this must be equal to rho cp dou t by dou t. So the unsteady term, temperature variation with respect to time, is on this right hand side, right? And the heat capacity rho cp. So we have to simplify this equation for the case of a one-dimensional heat conduction, steady one-dimensional heat conduction with internal heat generation, right? So to do that, let us say first case. So case A is you have a slab like this who has got the same temperature on both sides. So let us call this temperature as the TW, wall temperature, TW, same temperature on both sides. So these two points are at the same level. And this is the center line of your slab. So x is measured from this center line, and this is positive side of the x. In this direction, x is positive. Clear? And then K is the thermal conductivity of the material, and this Q dot is the volumetric heat generation rate. So unit of Q dot is watt per meter cube. So you can have the systems where there is internal heat generation part. You have to account for that, right? Now, how to simplify this? See how it is simplified. The heat diffusion equation. We have said one-dimensional heat conduction. So this term will go out, this term will go out, and this term will remain as it is. And we have considered k to be constant. So this k is taken out of this derivative here. k, and then you divide this entire expression steady state. That's why this is also 0, and q dot will remain because we are considering the internal heat generation here. So if you divide this expression by k and rewrite this equation, you can write d square T by dx square. Now temperature is function of x alone. It is not function of time. So partial differential can be replaced by total differential. That's why d square T by dx square plus q dot by k. Now this k, after dividing, here you will have 1 power k. That's why q dot by k is equal to 0. This is the simplified form of the heat diffusion equation for one-dimensional heat conduction with internal heat generation. Integrate this equation twice. Follow the same procedure which we did with the first case without internal heat generation. Same procedure we have to follow. So this T will be equal to minus q dot by 2k into x square plus c1x plus c2. c1 and c2 are two constants of integration. Now to evaluate c1 and c2, you need two boundary conditions. They are given on the screen now. So this boundary condition is at x is equal to minus L, you are at this phase. So this is x equal to minus L. What is temperature T? The temperature T is equal to wall temperature TW. Same way, at x is equal to L means you are at this phase, x equal to L. Temperature T is equal to again wall temperature TW. These two are same, same temperature. That is what our case 1 is. So if you use these two boundary conditions, then you will get the value of C1 and C2 like this. C1 will be 0 and C2 will be TW plus Q dot L square by 2K. Fine. Now, what is next step? You have to put values of C1 and C2 in this temperature distribution equation and rewrite the temperature distribution equation. Correct? To do that, the temperature distribution will look like this. So T is Q dot x square by 2K plus TW plus Q dot L square by 2K. Don't write all these equations. I am going to upload the slides. So temperature T will be equal to TW plus this term, Q dot by 2K L square minus x square. So this is our equation 6, right? So this equation will give you the temperature distribution along the length of your slab, right? Remember, this x is measured from the center. Remember this part. So the maximum temperature is observed at the center line, that is at x equal to 0. You need not have to do engineering to understand this. This is common sense. So suppose if you have the bounded conditions like wall temperature is same on both sides, right? And there is some internal heat generation, then by default the maximum temperature will be at the center only, right? You need not have to do engineering. So let us check. So if you put x equal to 0, then you will get T equal to T max. So the same thing is done here. So T max is calculated. This T will be replaced by T max if you put x equal to 0 here. So you will get this expression for the maximum temperature, TW plus Q dot L square by 2K, this term. Now, so if you look at equation 6 and 7, you can write this equation, temperature distribution, dimensionless temperature distribution. So this T minus TW. So this TW you can take on the left hand side, T minus TW is this term divided by T max minus TW is this term. So this term divided by this will give you 1 minus x by L whole square, or x square by L square you can write, right? So what you see from this is the temperature distribution is parabolic. Get me or not?
Yes.
Okay. So this equation is nothing but the temperature distribution along the length of your slab. Now this is worth noting down. With heat generation term, the heat flux is no longer independent of x. Remember this. With heat generation term, the heat flux is no longer independent of x. Is it clear how we determine the temperature distribution? Hello. Now can I go to next slide?
Yes.
Now, continuing further from the case 1, the one where we have considered the wall temperature TW on both sides, you can add one more condition to this. So what that condition could be, can assume convection on both sides of the slab, right? So use the convection boundary condition on both sides of the wall. So what you should do is, if there is convection and temperature of the fluid and the heat transfer coefficient is known on both sides, the wall temperature can be expressed in terms of fluid temperature and H. So the idea is this wall temperature can be represented in terms of or as a function of the temperature, fluid temperature, let us say T infinity or Tf, and heat transfer coefficient H. So you can express this wall temperature, and to do that you have to use this energy balance equation. So writing the energy balance, now this is what is this term Q dot AL?
So
What is
Q only, I think.
So it is rate of heat transfer basically, right? Q dot into AL. This is volumetric heat generation rate multiplied by the volume, right? The volume will go out, right? So you can write the energy balance Q dot AL means whatever it is conducted, this must be convected under steady state. So same thing I am writing here. Q dot AL is HA TW minus TF. TF is fluid temperature, TW is wall temperature. H is heat transfer coefficient and A is the area of the slab. So if you take this into account, then TW wall temperature can be represented as function of fluid temperature and the heat transfer coefficient H by this expression. So TW will be TF plus Q dot L by H. Is it clear? So previously we derived this equation, T is equal to TW plus Q dot by 2K L square minus X square. This equation we derived in the last slide. So here, when you are taking into account the convection on the sides of the slab, you have to replace this TW by this equation. So that is what is done here. So this TW is replaced by this term. And then we are writing that T is TF plus Q dot L by H plus Q dot by 2K L square minus X square. Clear?
Yes, sir, clear.
Let us talk about the second case, case 2. Now the same procedure we are following, the same equation is taken, heat diffusion equation. In case 2, what is different is the different temperatures on both sides of the slab. So look at this. We have the temperature T1 on the left hand side, temperature T2 on the right hand side, and then there is internal heat generation within this slab, which is shown here. K is the thermal conductivity of the material, and again X is measured from the this slab center, and this time 2L is the length taken. I remember this. So here X is equal to L and here X is equal to minus L, right? And the temperature T1 is greater than T2. T1 is greater than T2, and then there is internal heat generation. So this kind of temperature distribution you will observe, and without solving I am saying that the maximum temperature will be observed on the left hand side of the center here. Why? This is maximum temperature. This is more temperature than T2, no? So logically, without doing any kind of analysis, I can argue saying that the maximum temperature will lie on the left hand side of this center or not.
Yes, sir.
You do not have to solve it. You should understand this from common sense. Now the equation is simplified like this: d square T by dx square plus Q dot by dx equal to 0. And I am using the integration part, integrating this twice equation, you will get this equation. The only thing is you have to change boundary conditions again and again, and you will have the next case. So here, same boundary conditions are used. Only thing is at x equal to minus L, you have T is equal to T1, and at x is equal to L, you have T is equal to T2. Right? Use those boundary conditions, find out constants C1 and C2. Back to the temperature distribution equation, which is this equation, you will get this kind of temperature distribution. So this gives you temperature distribution. So T is Q dot by 2K L square minus X square plus T2 minus T1 by 2 X by L plus one more term T1 by T2 plus divided by 2. Right? Now, to find the maximum temperature, now this is the interesting part. So in previous case, it was simple that we know that the maximum temperature will be at the center line. But how we locate this distance x where this T will be maximum? So to do that, what we have to go through is differentiate this temperature distribution equation, right? Differentiate temperature distribution equation with respect to x and equate it to 0. So you have to write this dt by dx equal to 0. Means you have to differentiate this whole expression, equate it to 0. And then whatever value of x you get after doing this, whatever value of x you get, put it back to this equation. Then T will be replaced by T max. Is it clear?
Yes.
So doing that, you can find out whatever expression you get at the end. Now I am not going in details of those mathematical steps. If you try to solve even the problem based on this kind, you have to go through this procedure only. Don't try to memorize the equations. Better try to derive them. Go through the basics all the time. So idea is differentiate this with respect to x, equate it to 0, and find out the value of x. Whatever value of x you get, put it back to this equation, then T will be replaced by T max. As simple as that. Now, if you use the convective boundary condition, then what you can do is these temperatures T1 and T2 can be expressed in terms of fluid temperature Tf. So you can assume the fluids like having temperature Tf on this side and Tf on this side, call it as Tf1 and Tf2, something like that. And then you can express this temperature T1 and Tf, T1 in terms of Tf and T2 in terms of Tf2 on other side. So this we have already talked about in the previous slide. This we are getting from energy balance. Do you remember this? That Q dot AL is equal to, we are writing that term, right? Heat, whatever heat is conducted is convected to the surrounding. Are you getting my point or not? So we know how to use this. We had derived this in the previous slide. So simply T1 will be replaced by Tf1 plus Q dot L by H1, and T2 will be replaced by Tf2 Q dot L2, L, it is same, L divided by H2 on this side. So this is how you can invoke the convection boundary condition in this case also. Is it clear? Hello? Is it clear? Second case. Hello? I think not a single student is attending lecture.
सर वो T equal to Tf plus Q dash L by H उसका मतलब यूज किधर करना है सर?
See, if you consider convection, let us say convection on both sides of this slab, So here you can have the fluid having temperature Tf1 and heat transfer coefficient H1, right? So using this expression, I am representing this temperature T1 in terms of Tf1 and H1, no? Get me or not?
Yes sir.
Similarly, you can do the same thing on right hand side also. This is what I am saying. Let's talk about the last case in the plane ball. So the third case is one face is perfectly insulated. So here is the situation. You have the slab like this. This face is insulated, the left face. And then what you see on the right hand side is only wall temperature T, and there is internal heat generation Q dot. So again, you need not have to do engineering to understand that the maximum temperature will be observed at this phase, and then the temperature distribution curve will look like this. Fine, and you can consider convection on this side as well. If you want, you can consider the convection. Fine. How to solve this? So again, I am simplifying the heat diffusion using the boundary conditions. Now, boundary conditions is important. I will use boundary condition. So, the first boundary condition is at x is equal to L minus L. So I am again taking the x from this position. So this is at x equal to minus L. This dt by dx will become 0. The gradient will be 0. Now why temperature gradient will be 0? Because no heat is transferred in this direction. So this is 0, no? Right? So if I reach this point, the slope of this temperature distribution curve must be 0. So if I draw a tangent at this point, which represent the this gradient dt by ds, this must become 0. So it means this tangent must be horizontal, right? So at x equal to minus L, dt by dx is equal to 0. This is first boundary condition here. And the second boundary condition at x is equal to L means at this phase, temperature T is nothing but wall temperature T. So this is the only difference. Pretty similar to what we did in previous two cases. We'll find out constant C1, C2, this equation, derive the expression for the temperature distribution T like this, and again the same procedure. So to find out the maximum temperature, what you have to do is differentiate equation 5, this equation with respect to x, equate it to 0, and by default you will get x equal to minus L in this case. You should get x equal to minus L because we know that temperature is maximum at this level. So you will get x equal to minus L once you differentiate this into. Then you can invoke the convection boundary condition on this side. So you can replace this wall temperature Tw as Tf into Q dot L by H, or here they have written Ta, so you call it as Ta and this as Ha. Or you can change the notation to Tf and this as this as H and this is Tf. And use the same Tf plus Q dot L by H. So that it will be similar to the previous case. So that's all about the three cases of a plane slab with internal heat generation. Similarly, you can do the analysis for the hollow cylinder with internal heat generation, and then again this kind of conditions. The three cases, that is same temperature on both faces, then the different temperature of both cases, and the one face is insulated, right? So you can have in cylindrical system, you can have the inner face insulated or you can have the outer face insulated. So depending on which face is insulated, your analysis is going to change because your boundary conditions will change, correct? And similar kind of exercise you can do for the hollow sphere also. So all that stuff I leave it to you to explore further. Heat transfer is very vast subject. If I keep on talking about each and every case, your term end will happen only in conduction. So with all those limitations, now I think we should stop discussion on this internal heat generation part. You can take down one numerical based on this. I have the solution. I will directly explain the solution. You need not have to take down anything. You can try it at your end at the end of this session. So here is a numerical based on internal heat generation. So heat is generated uniformly in a stainless steel plate having the thermal conductivity. K of this plate is given, which is 20 watt per meter K. The thickness of the plate is 1 centimeter, and heat generation rate is this volumetric heat generation rate Q dot 500 megawatt per meter cube. We should convert it to watt per meter cube. If the two sides of the plate are maintained at 200 degrees centigrade and 100 degrees centigrade, means this is case. Which case? This is case 2, different temperatures, right? Calculate the temperature at the center of the plate, means this, what is temperature T, then the position and value of maximum temperature. So it means you have to find out this X where T is T max. So both things, T max as well as this X, you have to find out the position and the value of maximum temperature. And then next, the heat transfer at the left and right faces, means what is this Q? See, if there is internal heat generation, then part of heat will go in this direction and part will go in this direction. So you have to talk about the heat transfer at left and right faces as well. You have to find, and then sketch the temperature profile in this lab. Now with this I have already plotted, but however In examination, you have to plot it on your own. This diagram I have given for ready reference because I don't want to spend much time discussing this problem itself. Fine. So with this given data, how you will solve the case of the internal heat generation, slab with internal heat generation and two different temperatures on the left and right hand side case of the slab. This is known to us. You know the temperature distribution like this. I am taking the same. And using the boundary conditions like this, we know C1 is given by this expression. So I can find out C1. It will be given by this expression. I know this. Now, why I am writing all these steps is, in examination, you should not try to memorize the equations. So don't try to memorize the equations C1 and C2. You should be in position to derive those and then put the values like this. And then simply find out what is C1 and C2. So next is, once I know C1 and C2, I am going to put it back here in equation 2 and write it in. So putting C1 and C2 in equation 2. Write the temperature distribution equation. This is my temperature distribution equation. This one. How the temperature is varying with X. So that equation, quadratic equation. Now next is, I need temperature gradient, that's why I am differentiating this with respect to X. So dt by dx will be like this. Temperature at the center. So if I put X equal to 0 here, X equal to 0, then this T is nothing but the temperature at the center. So T at X equal to 0, or this is center temperature, right? So this is 462.5 degrees C. So this will become 0, correct? So first part is over, temperature at the center. So to find X at which T is maximum. Now same procedure, differentiating this equation 3 with respect to X and equating it to 0. So I am writing dt by dx and equating it to 0. Means I have to equate this to. So if I equate this expression to 0, I can find out this X. So let us call this as X max, right? So X max I am denoting in connection to the temperature T max. So I am getting that value of X which I specified in this diagram, X at which temperature becomes T max. That value turns out to be minus 0.0004 meter. This minus sign indicates it is on the left hand side of the center line. And then if I put this value here, so I will get this temperature T max. So T will be replaced by T max. So this temperature will turn out to be 464.5 degrees. Now, heat transfer from the left face. So we know this is our slab. This temperature is higher and this is lower, and the temperature distribution will look like this. We talked about this. So we have to find out this heat transfer from this slab Q1, this side of the slab, and heat transfer from this side of the slab Q2, right? So I'm writing the Fourier's equation. Q1 is minus k dt by dx at x equal to minus l. Means I'm talking about this space, minus k dt by dx at x equal to minus l. So I'm taking the area per meter square, 1 meter square area, and I know dt by dx, so I can put x equal to minus l here, and simply find out this dt by dx, put it here, and then you will get this, that the rate of heat transfer from this space is minus 2300000 watt, right? We can write it in kilowatt or megawatt hour. Now, the heat transfer from the right face I am calculating Q2. So again I am writing the Fourier's equation. Q2 is minus Ka dt by dx, but this time it is at x equal to L, means at this temperature gradient at this level, x equal to L. So I know dt by dx, I am going to replace this x by L, and then I will get the value of the heat transfer somewhere around this 2700000 watt, right? Now see the consistency in the sign convention. This side Q1 I am getting negative sign, which is obvious, and for this the heat transfer will take place in positive x direction, so I am getting the positive sign. This is also obvious, right? Get me or not? Hello?
Yes, sir, yes.
Okay, fine. Now what is the heat generation rate in this case? They have mentioned. So this is 500 megawatt per meter cube, right? Correct? So if if you look at the values of Q1 and Q2 and compare it with the volumetric heat generation Q dot, so if you multiply this Q dot by Q dot into AL is 1 meter square, and this length, so you have to take this total length. So this value will match with the these two values, Q1 and Q2, right? So check here. So this is final check. So Q total will be the mod I am taking, not the signs here. So if you see the magnitude of these two, sum of these two must be equal to this Q dot A into L. So as I said, L you should take the total length, and we are measuring L from the center. So this total length we assume 2L, remember this, right? So if you put that here, it will be this term. So this is how you should cross check at the end. So that's all about how to solve the problem with internal heat generation. I explained you the entire procedure how to do this. Now same logic will be applied for other two cases, like same temperature on both sides and one face insulated. So even if I change the problem, you should be in position to solve it. I have only taken one sample example of the second case, different temperatures. If you plot the different temperatures, they will look like this. So this is your left face of this slab, this is the right face of this slab, and you are getting the maximum temperature 4.5. Somewhere you will see, somewhere here you will see that maximum temperature, right? And somewhere here, let us say this one. This is maximum temperature 464.5 degrees C, and then at center line temperature 2.5. This temperature must be 462.5. So you can see this through the plot also. So, is it clear?
Yes, sir.
I think we are running out of time, so I should stop now. Now there are few more cases remain to be discussed. So again, I will take at least one lecture on this, and then one-dimensional heat conduction with generation part will also be over. So we have lecture on Monday, right? So Monday will be last lecture for this.
So for this module?
For this case, one-dimensional heat conduction. So you can check the syllabus.